All right, I'm going to be writing up my set of solutions for a series of questions that were released by Bedford Freeman Worth, generally referred to as BFW. They publicly released these questions, so I strongly encourage you to take advantage of that. They're not official College Board questions, but they're of a very similar nature, very similar difficulty. Really good practice for you, especially since these questions have never been seen before. They're actually brand new. So I put a link in the description below to get the PDF of the questions themselves. If you haven't seen the questions yet, I'd encourage you to download the PDF and spend some time with the questions on your own before continuing on with my solution video. That way you will really maximize your experience with these questions and see how you did. Okay, with that said, I'm going to get right to work here. Number one. We have, in this question, students who are to carry out a series of experiments with blocks in a lab. For the first experiment, some students decide to use a launcher to give both blocks the same initial velocity v0. Okay, so just kind of highlighting things so I can keep track of them. So there are two blocks, and they have the same initial velocity v0. They launch them across a table. The coefficient of friction between the table and the blocks is given as mu, and we're further told that the blocks are made of the same material. So the blocks are sounding identical so far, but the difference is coming up right now. It says, but the mass of block A, designated MA, is twice the mass of block B, MB. Now, what I sometimes like to do when I get information like this is record it as an equation. To do that here, I would say something like this. The mass of A is equal to twice the mass of block B. Now, the equation I just wrote, I think, is correct in describing how these two blocks compare to each other, but let me just take a moment here to explain what I have seen as a very, very common mistake, so that if you were at all tempted to do this, hopefully you're going to be aware of this not to make this mistake. So some students tend to read a sentence like that and basically get it backwards. So if you were tempted to write this, and again, what I'm about to write is wrong, but just let me talk about it. 2MA is equal to MB. So probably the reason some students would write it that way is because they see twice here, and twice seems to be attached to MA, at least verbally within the question. It seems to be that way, right? So I can appreciate how somebody might put, 2MA as being kind of the equivalent of that. But notice how that is precisely backwards. For example, let's say that the mass of B was known to be, I'm just picking a number here, let's say that it was 6 kilograms. Okay, so according to this equation, which again I'm claiming is not correct, you'd have to figure out what the mass of A is by dividing the 2 to the other side, right? That's the mass of A would be equal to mass of B divided by 2. So if mass of B was 6 kilograms, that would make the mass of A 6 over 2, 3 kilograms. So notice by this line of reasoning, it seems that B is the more massive of the two. And that's wrong. We know that MA is twice the mass of B. So whatever B is, you have to double that mass in order to get the mass of A. And notice that that is exactly what I've written over here. Whatever the mass of B is, so if B was, just to use this example of 6 kilograms, then the mass of A would be 2 times 6 kilograms, 12 kilograms. So just to throw that out there, I've seen that happen way too many times with students making that mistake. So hopefully that will not happen to you. All right, let me just get rid of this stuff here, clean up my mess that I made, and continue with the question itself. There we go. Highlights, just keeping the highlight that I need and all of that irrelevant stuff gotten rid of. So part A, subpart 1 says, student 1 says that block A will slide farther along the table before coming to rest. So this is a claim made by a student. Anytime you read anything along those lines, a student, claims the following, or a student comes up with the equation, or they look up on the internet and they find something, that usually means that there's probably some level of uncertainty here. It may be correct, it may not be correct, and often one of the things that we're going to have to do in the question is determine that. Okay, but if you've seen any of my previous videos, you've heard me say to just focus on the question that is being asked, answer the question you're being asked, and move on. So let's focus on what A1 is asking us to do. Student 1 says that A will slide further along the table before coming to rest. The question is right here. What reasoning would support this prediction? So notice that we are not being asked, is this correct? Is this not correct? Why or why not? What should it really be? We're not asked to do any of those things. We're simply asked to provide any line of reasoning that would, on its own, support that. So again, there could be other factors that are going to come into play that negate this, but we just have to find something that would say, well, if you focus on this one parameter only, yeah, you can kind of see how that might play out. Although, as you see in later parts of the question, this is going to be fleshed out more fully in a minute. Okay, so the student is claiming that A will slide farther. Okay, so A, of course, is the more massive one, right? MA is twice the mass of B. So this is the, I'll just say, heavier, by which I'm really thinking more massive, etc. So if they're given the same initial velocity, why might the more massive one slide farther? Can we think of any line of reasoning that would at least support that in exclusion? Well, by saying twice the mass, or for that matter, heavier, probably the most relevant factor that I'm thinking of is inertia. Inertia is that property of an object, of its mass, that would try to enable it to resist any changes to its motion. So if it is moving, it will tend to maintain that motion. So by being twice as massive, it is also twice the inertia, which means that it's basically twice as hard to stop. So I'm going to suggest that that on its own supports this student's reasoning. Okay, so let's see here. I can write this up as something like this. Block A is twice as massive as block B, and so has twice the inertia. It will be harder to slow A down to a stop. So all else being equal, and of course the devil is in the details because I don't think that all else really is equal, but if all else, in fact, how about if I even put a little if in there? So if all else being equal, it could, kind of, again, being a little bit loose here because I've already thought this through and it is not going to slide farther. It could slide farther because of this. All right, that's probably enough for that. The next part says, student B says block B will slide farther. So again, that's the less massive one. So there's direct competition here with the other student. And once again, we're asked, what reasoning would support this prediction? Well, let's think about this. This block is lighter, and considering that it is the same surface, it's the same coefficient of friction, being lighter in this context is genuinely going to lead to a reduced force of friction to stop it. So if we think of that and that alone, we might reason, well, I mean, with less force of friction on it, it's going to slow down only more gently, and so maybe it'll slide farther. Again, kind of putting a little bit of an if in that, if all else was equal. So I'm going to build my answer around that. Being less massive, block B will have a smaller weight, and in this case, a smaller normal force. So the force of friction will be smaller on B as a result. So it has less force of friction trying to slow it down to a stop. So I think I'm going to word this similarly to how I worded the previous one. If all else is equal, the lesser force of friction on B could result in it sliding further. So yeah, less force of friction on it. If you don't think about anything else, you might say that that supports the prediction. Part B says, never mind what those students think, we're on our own for this one. We are to derive a mathematical expression that we could use to find the distance traveled by a block, specifically it says block A, after it leaves the launcher in terms of the given quantities and physical constants. So given quantities are ma, v0, coefficient mu, and the only other thing, physical constants. So lowercase g qualifies for that in this kind of a question. So derive an expression. Okay, so I'm just going to solve this the way I would solve any kind of typical problem. I'll support it with a bit of a diagram here. So here is specifically thinking block A, so I'll say that's the mass of block A. This is not a free body diagram, it's just really me supporting my work here, so I'm not going to limit myself to the usual rules of a free body diagram. I will certainly show the forces, so there'd be a force of gravity on block A. There'd be a normal force on block A. And if I just think of it as moving this way, so let's just say it's sliding to the right, then there would be a force of friction to the left. That would be it for forces. It has already left the launcher, so any applied force to get it moving has been removed, as it is now just on its own sliding ultimately to a stop. So this is while sliding, not yet stopped. So basically, this is a pretty familiar situation. If you've done any number of force problems, you've seen this like a dozen times at least. So I'm just going to do this quickly by saying in the Y, this is just how I symbolize a vertical kind of analysis. I'm just going to say this quickly as it is certainly not accelerating vertically. It's not going up or down, for example. So I feel confident in saying that we have a balance of forces. The force normal on this block is equal to the force of gravity on this block. That means that the normal force is equal to the mass of A times g. By the way, the normal force is not always equal to the weight of an object. That's a big pet peeve of mine. But in a simple situation like this, it can be. And in this case, it is. The normal force is indeed equal to the weight of this block. Now, meanwhile, in the horizontal, this thing very much has a force of friction, and so it is going to slow down. So the acceleration would be equal to, in fact, let me just be very specific here. If I use to the right as my positive direction for x, then I can say that the acceleration is net force divided by mass, and the net force is a negatively directed, so I'm going to put a negative in here because it's to the left in my diagram at least. So the force of friction divided by the mass of this block. In fact, let's put subscripts in here for A. I'm specifically focusing on block A right now. So the acceleration of A is equal to the negatively directed force of friction over mass of A, and that is equal to the negatively directed mu times the normal force on block A divided by the mass of block A. And this is equal to the negative mu times, I'm just going to cheat and give myself a little bit of extra space here because I don't have a lot of space in this problem. I kind of spaced this out myself and didn't give enough space, so I take blame on that one. But nonetheless, this should work. So mu times m of A, go back to my pen, mass of A times g, all of which is over the mass of A. And you will notice that the mass of A drops out of this equation. So the acceleration of this block as it comes to a slowdown is equal to negative mu g. In fact, let me just record that, negative mu g. And again, that negative is there is because it is slowing down and I've used the forward direction as positive. Okay, now don't forget to answer the question. It would be tempting to say, wow, look at that, the mass dropped out, I'm done, and I can imagine a student just quickly moving on here, but hold it, what were we asked to do exactly? Derive. Okay, so I'm very much deriving. Deriving means starting from first principles and kind of letting the math happen to the specific situation here. Hang on, the distance traveled by block A. Right now I only have the acceleration of block A. So if you want me to find the distance traveled, I'm not done yet. So let me continue on here. Now that I have an expression for the acceleration, maybe I could just use kinematics to find an equation for the distance traveled by block A. To do so, I'll just say we know that the starting velocity, I'll use a v initial, that's the notation I often like to use here, is designated v0 in this question. So on the left is my generic and on the right is the specific to this question. We know that it's going to continue to slide until it stops moving, so vf of 0, and the question is, at least algebraically, what's the distance, or in my line of thinking here, the displacement, but I'll report it as magnitude only for distance. Okay, so a kinematics equation that links these variables together is vf squared equal to vi squared plus 2ad. So if you want the distance, or really displacement here, just solve this equation for d. So d is equal to vf squared minus vi squared, all of which is over 2a. Now again, that's just generic kinematics, and it's okay if you use a notation that's a little bit different. If you're using a delta x for displacement, that's totally fine. This is just my preferred notation. But in this question, or in this situation, the vf is known to be 0. So 0 squared, subtract v0 squared, all of which is over twice the acceleration. And the acceleration I know to be negative mu g. Negative mu g like that. And this is going to simplify to d equal to, notice how negative numerator and denominator will drop out to become positive. So v0 squared over 2 mu g. All right, now I got a little bit sloppy on my subscripts here. Just to be very clear, this is the distance, magnitude of displacement, that A will move. So there we have dA. But an interesting thing that's going to be relevant right away in part C is to notice that there's nothing on the right side of this equation that is unique to block A. Block B shares the exact same V0, the exact same coefficient mu, and of course is in the environment with the same G value, 9.8 for both. So even though I wrote this up for block A, there's nothing unique to block A. It doesn't really matter that the masses of the two blocks are different. So bear that in mind as I now go into part C. Part C says, does the expression you derived in B, the equation we just finished with, in fact maybe I'll just keep it on screen a little longer, does it support the reasoning you used in part A to support either student 1 or student 2 or both? Briefly explain. So does it support the student reasoning? Well, I mean, there are elements within, but the end result, I'm going to have to say, is not. So is there any line of reasoning? How about if I say, within the derivation, we can see from Newton's second law, which I'm just going to write as A equal to net force over m, that acceleration is proportional to net force and inversely proportional to mass. So does it support either student 1 or student 2 or both? How about if I just say these elements on their own support both students lines of reasoning, but I have to qualify that by saying, but taken together, neither students let's say conclusion is correct, as the acceleration and so distance in this case is not dependent on the mass of the block. So both blocks would be expected to slide the same distance. All right, so did I answer the question? Does the expression you derived in B support the reasoning? In a way it does, but it's only in a very, very partial way. In the end, both students are wrong. So I think I have said everything I want to say there for part C. Moving on to part D, which is the last part of this question. The situation is fundamentally changing here. We now are only looking at one block. And the question says, in a second experiment, you decide to connect a string which has length L. Okay, so you can see that string right there. The string has length L from a pivot to the side of block A. Okay, so there is a bit of a nuance here that I think would be easily missed. We're connecting that string to the side of block A, which has a width designated as lowercase d. So we typically default to assuming that objects are small, okay? Like the size we often assume is completely negligible. That's not the case here. I mean, they're specifically calling out that that block has a width that is not negligible. So maybe just to enhance our understanding of that, let me draw a slightly bigger version of that. So suppose that this is that block, just drawn a little bit bigger. The string is connected to one side of it, and we can see that the width of the block is designated as d. The importance there is in realizing that as this block moves, it does so in a circular path, but we really need to measure the size of that circular path with respect to the center of mass of that block. And you can see that if the string is of length L, okay, so if that's the length of the string, then the actual size of the circle moving is a little bit bigger, right? The circle would have a radius r, which is the length of the string and a little bit extra. We'd have to add half of that width of the block to get to the center mass of the block. So I'm just going to write that maybe as length plus 0.5 d. I often prefer to work with decimals over fractions, but that's a preference. Either way would be fine. So what's going on here? We got it connected, constrained to go to circular path once it leaves the launcher. Okay, so subpart 1. Write an equation for the maximum tension in the string during the motion in terms of the given variables and relevant physical constants, and justify its choice and the variables used. So we're to write up an equation and then kind of just justify it. So we do have to do two things here. We have to justify it. We also have to write this equation. All right, so, and it specifically calls out the maximum tension. Okay, now the reason it's calling out a maximum tension, just to be clear here, this block is not moving vertically. It's not coming down like faster, faster, faster. This is not a vertical situation. We're still on the tabletop. That was my understanding of it. It's a top view. So we're looking down. This thing is on the tabletop. And of course, we've already understood that there's a coefficient of friction here. So what's going to happen is this block is going to move, yes, in a circular path, but it actually won't be uniform circular motion, because that force of friction is going to cause it to slow down, slow down, slow down, slow down. At some point, I don't know where, but at some point it's going to stop. So just consider that. It's going to be slowing down. Yet at any one moment, the usual physics is going to apply. Uniform or not uniform, at any one moment in time, I can just think of those equations as being applicable. So if I think of circular motion, I can write that the acceleration is centripetal, but it has to be equal to the net force centripetal, in other words, directed towards the center, divided by the mass of this block. All right, so, in fact, just to be clear about that, did it say which block I have? Oh yeah, block A. So let's use M of A. So this is the acceleration of block A, but it's centripetal, so I'll just use it as AC. All right, so the maximum tension is going to occur when the block is moving fastest. It is going to slow down, but the fastest speed will correspond with the maximum tension. So at least for this question, I don't have to really focus on the fact that it's slowing down. I can just hone in on the maximum acceleration, which occurs when the thing is moving at its full speed, v0. So v0 squared over radius of motion, and that's, I had just talked about that in terms of the length as well as the width of the block, but I'll add that in a moment. So v squared over r is going to be equal to the only force that's pulling it towards the center. So if I just draw it at some arbitrary moment in time here, if this is the center of the circle, the only thing pulling it towards the center is that tension force. There would also be a friction force, but notice that that friction force has no component even directed towards the center of the circle. The force of friction is tangent to the circle. So it will be responsible for slowing it down, but the tension force is responsible for steering it into this circular path. So the net force centripetal, I can safely neglect friction for this for the reason that it's not in any way directed centripetally, i.e. towards the center. So this is the tension force, Ft, divided by the mass of block A. Now let's not lose track of what we've been asked to do. We're trying to write an equation for the tension, and we have to do so in terms of those given quantities. So I'm going to do two things here. I'll solve for the force of tension. Force of tension is equal to the mass of block A, V0 squared, over R. So that's just solving that same equation for Ft, but I will now substitute. Notice that R is not one of the given quantities, so I'm going to replace R with what that radius of motion would be equal to, and I have that up here in red, the length of the string plus that half of the block width. So this is equal to mass of A, V0 squared, and I'll change color only so that it's helpful to you. Again, don't do this when you're doing it on your own, but I'll do it for just clarity here. The radius R is known to be the length of the string plus half the width of the block D. So I think that's it. That's an equation for the tension force in terms of the given quantities. Each of these variables was presented to me, the mass of A, the initial speed V0, length of the string, and the width of the block D. So that's pretty good for that, but don't lose track that I also have to justify what I've done here. So during the motion, in terms of variables, relevant physical constants, and justify its choice and the variables used. Okay, so let's justify this, and I've already done this verbally to some extent, so I'll just add it in here. I'll say the tension force alone acts to provide the centripetal force, and so is the net force centripetal. A lot of people would just call that the centripetal force, but I'll just clarify that that is the net force. Okay, so there's that. So that basically justifies my choice for the Ft here. Let's also just justify my choice for this L plus 0.5d. So let's clarify that. The radius of motion to the block's center of mass. Okay, so just stressing that center mass would be the length of the string plus 1/2 the block's width. And I think that should do. They've only asked me to justify its choice and the variables used, so I think that probably will do the trick. Moving on to the last question here, the last part of the question, it says qualitatively. So the word qualitatively means just descriptively. You don't have to use any numbers. You don't have to use any math. Just describe in words is what qualitative means. Qualitatively describe how the tension in the string changes during the motion and explain why it's changing that way. You can see from my equation here even that the tension can be calculated in part based on the speed of motion, right? How fast it's going. Now, none of the other variables are changing. The mass of A is fixed. It's the block's mass. The string is constant in length, the block is constant in width, but because there is friction acting to slow it down, the reduced speed will result in a reduced tension force. So my answer is going to be, starting with that, qualitatively describe how the tension in the string changes. Okay, so I'll write that up as the block slides. Tension force would get smaller in magnitude. How the tension of the string changes during the motion and explain. I'm not sure that they're looking for it, but how about if, just for full clarity, I will say it will also change in direction as it will continue to point toward the center of the circle. Okay, so it's actually changing in magnitude as well as in direction. In terms of changing in direction, I don't think that that's anything to really explain any further that I already have, but let me just elaborate on how I feel confident that it's getting smaller in size. As the block slides, it slows down due to friction. As it slows, and I'm focused on that centripetal force, the tension force, as it slows, it changes direction of motion more slowly. And of course, realize that that's what centripetal acceleration is. Centripetal acceleration is that acceleration due to the change in the direction of your velocity, which way you're moving. So if you're moving slower around a circle of constant radius, then your direction of motion is changing more gradually. So it changes its motion more slowly, which is to say, I'll just say i.e., its acceleration gets smaller and the force of tension gets smaller with it. And probably that's adequate. So I think I'm going to leave it as that and say that my solution to this problem is finished. Hope that was of some help to you. I'll be working on the other problems as soon as I can.